see. Actually, let me finish this calculation we were looking at yesterday. And we're looking at the driving force for this H2O liquid going to H2O gas. And we saw that the delta G was positive. If the delta G is positive, that means delta H of the universe, not delta H, delta S of the universe is negative. And so that means a negative delta S of the universe. So in other words, this is non-spontaneous as written. Non-spontaneous. The reverse direction is favored. And so essentially this is boiling. Does water boil at room temperature? No, that's non-spontaneous. However, if we look at this scenario, the energy goes up, but so does the entropy. Energy going up is not favorable, but entropy going up is favorable. And so what we can do is we can bias the entropy term by increasing the temperature. We increase the temperature, that's going to make the entropy term larger. And eventually we should be able to cancel this out. So if we have a positive 44 here, then we just need a negative 44 over here. And so is there a temperature that will make that term negative 44? And so what we're going to have here is the delta G under standard conditions at 298 Kelvin is equal to 44.0 kilojoules minus T times, okay, I'm going to convert this into kilojoules, 0.11889 kilojoules per Kelvin. So if I can get this term to equal negative 44, then I'll have my positive 44 here being canceled out by negative 44. And so I'm just trying to cancel out the unfavorable energy term. Unfavorable. And if I can make this even bigger, that is more negative, like negative 45 kilojoules, then the whole thing will go negative. And so to cancel this out, what I'm going to do is I'm going to just set it equal to 0. That means I'll have a positive 44 and a negative 44, and then solve for T. In solving this for T, I'm going to get a T of, so this is going to be 44 divided by 0.11889. And the T comes out to 370.08 Kelvin, which is equal to how much in degrees C? Well, this will be minus 273.15, and I get 97, around 97.08 degrees C, approximately. Oops. And so what this is saying is this: if I can get this to 97 degrees C, then I can cancel out this unfavorable energy and then get this to go spontaneous, at least be in equilibrium. When we have H2O liquid in equilibrium with H2O gas, we call that boiling. And so essentially, to get it to 97, it should boil. What is the boiling point of water? 100 degrees Celsius. So this is off a little bit, right? It should be 100. And so why is it off? Should be 100 degrees C. Or should it be? Actually, this is not correct. It's not 100 degrees C because this temperature is for standard conditions. And standard conditions are for 1 bar. And so water does not boil at 100 degrees C under standard conditions. This is one of the reasons why I still prefer atmospheres. And so what temperature does water boil at under standard thermodynamic conditions? Do you have it memorized? No, neither do I. So we'll have to calculate it. So how can we calculate the boiling point of water, well, under standard conditions? Standard conditions are 1 bar versus 1 atmosphere. And so we know that there are 1.01325 bar in 1 atmosphere. And so if we're at 1 bar, then we're slightly lower than 1 atmosphere. And so if the pressure of the atmosphere goes down, what happens to the boiling point? It also goes down, yeah. So water boils at lower temperatures, at lower pressures. And so cooking instructions, like high altitude cooking instructions where the pressure is lower, are longer. We need more cooking time. So how can we figure out at what temperature water boils at a different pressure? And so we have to think back to Chem 1A. Do you recall anything from Chem 1A that will allow us to figure it out? One of the things that you may recall are the vapor pressure curves. Do you remember vapor pressure curve for water, what it looks like? And that is, we have the vapor pressure here, we have the temperature here. What was the shape of the curve? Pressure versus temperature. Was it a straight line or was it a curved line? It was the curved line. And then we had something called the normal boiling point. The normal boiling point was when the vapor pressure was equal to what pressure? 1 atmosphere. When the vapor pressure was equal to 1 atmosphere, then we had the normal boiling point. Because this was the boiling point under normal pressure being 1 atmosphere. But what happens if the pressure goes down? Well, if the pressure goes down, then the boiling point goes down as well, according to the curve. If the pressure goes up, the boiling point goes up. So pressure cookers, you want high pressure so you can get hotter temperatures and cook the food faster. And do you remember the equations for this curve? One of the equations is a very famous equation from chapter 12. have it here, I think. Does this equation look familiar? Equation 12.2. This is one of the forms of the Clausius-Clapeyron equation. Okay, I'm signed out. This is exponential, and so we can rearrange this, take the natural log, and we get the ln of P2 over P1 is equal to minus delta H of vaporization over R 1 over T2 minus 1 over T1. So we know the vapor pressure of one of these, that is, we'll call that P1 or P2. Actually, let's solve for P2. And therefore, P1 is going to be the normal boiling point. I'm going to do this in bar. So this is going to be 1.01325 bar. If the pressure is 1.01325 bar, then the temperature should be 100 degrees C, or 373 Kelvin. However, our pressure is a little bit lower. Our pressure is exactly 1 bar. So I'll just do 1.00 bar. And I want to know what the temperature is here, T2. I guess that doesn't really matter. I should solve for T2. Or no, I'm solving for T2. All right, so let's just plug in the numbers. ln of P2 is it's going to be 1.00 over 1.01325 is equal to delta H of vaporization is just the delta H that we just looked at, which is minus 44. Delta H is a positive 44, so it's negative times a positive 44.0 kilojoules. This is kilojoules per mole of water, so I could either write kilojoules or kilojoules per mole. Since R is in units of joules, I'll just do 8.3145 joules per mole Kelvin. And then what I'm going to do is I'm going to convert kilojoules into joules. So I'll just do 1,000 joules per kilojoule. And then I have 1 over T2 minus 1 over T1. T1's 373 Kelvin. All right, so let's solve this for T2. And so let me take the I'm going to take the natural log, ln of 1 divided by 1.01325 quantity divided by negative 44. Divided by 1,000 times 8.3145 plus 373 inverted equals, and then I'm going to invert my answer to get this. And so I got a T2 equal to 372.65 Kelvin, which is equal to, okay, minus 273. 0.15 if I want. 99.5 degrees Celsius. So under standard thermodynamic conditions, water boils at 99.5, not 100 degrees C. And so it's a little bit closer. My calculation was 97 degrees. I'm still off. And so that's what it should be. I calculated 97 degrees. And so it's off. Still off. Now, what do you think that's attributed to? That's attributed to this. We're making the assumption that delta H at 298 Kelvin is the same as the delta H at 373. It's an okay assumption, but it's going to be off a little bit. And we're also making the assumption that delta S at 298 Kelvin actually is the same as delta S at 373, actually 372.5. 372.5 is what it should be. So it's going to be off a little bit. So again, we're using the wrong delta H and the delta S. And we're using the wrong delta H and the delta S because we don't have the correct ones. What's that? Therefore, it's probably off. That's probably what's throwing it off. All right. So this is a more reasonable temperature to achieve. Now, it depends on what delta H and delta S are, if they're positive or negative. Temperature could be used to actually reverse the driving force, like in this case. The driving force was for the backwards or the reverse reaction, not the forward reaction. And by adjusting the temperature, we were able to change the driving force to the forward direction. So we need a temperature greater than that. And then the forward reaction should be spontaneous. That is, I'll take my positive 44 and at this temperature, it should give us a negative 44 and cancel that out. And then at temperatures greater than this term will go larger than negative 44. That is negative 45 or whatever, etc. And make this spontaneous. All right, any questions on this? Okay, I need to post this for you, Andrew. All right, let's take a look at today's lab. Actually, before we take a look at today's lab, let's take a look at the synthesis lab. And let's take a look at reaction 1 in more detail. Did I already do reaction 1, the balanced chemical equation for reaction 1? Reaction 1, we're taking the dichromate and reacting that with oxalic acid. In what forms? Well, in what form does the dichromate gets what we say reduced to chromium 3. So we went from chromium 6, or hexavalent chromium, to trivalent chromium, chromium 3. And then what happened to the oxalic acid? The oxalic acid got oxidized. And so we went from carbon in the +3 state over here in oxalic acid to carbon in the +4 state in CO2. So we generated some CO2 gas. You might have seen bubbles coming off. And the color did change, from orange dichromate to chromium 3. It was kind of more black, blue, I think, isn't it? This is what we call a skeleton redox reaction. In a skeleton redox, we just mix it together and see what happens. So we mixed it together, saw what happens. These are the major products. So in skeleton redox, the first step is we separate it into 2 half reactions. So the first half reaction is the dichromate. The dichromate ends up in chromium 3+. And the second half reaction is the oxalic acid. The oxalic acid is going to end up as CO2 gas. So these are our 2 half reactions. And then we balance these. So starting off with the dichromate first, I have 2 chromiums and 1 chromium. And then I'm going to balance it by changing the coefficient here. I'll just have 2 Cr3 pluses. And now I have 2 chromiums on both sides. Okay, after I balance chromium, which element? Well, there's only oxygen. So I have 7 oxygens and 0 oxygens. So how do I balance out the oxygens? I'm going to add H2O, and I'm going to add 7 H2Os. So if I add 7 H2Os over here, it's going to give me 7 oxygens. Okay, after I balance the oxygens, then what do I balance? Hydrogen. So there's 0 hydrogens on the left, and there's 14 hydrogens on the right. How do I balance out the hydrogens? What do I do? Yeah. And so I need to add 14H plus to my dichromate. Okay, after I balance out the hydrogens, I'm going to balance out the charge. So plus 14 minus 2 is plus 12. And then over here, 2 times plus 3 is plus 6. Water's neutral. And so what I'm going to do over here is I'm going to go ahead and add 6 electrons. So I'm going to put 6 electrons. 6 negative charges will cancel out 6 of the positive charges. So I have plus 6 is equal to plus 6. That's what I want. And I'm going to combine everything. So when I combine everything, I'll get the 6 electrons plus 14H plus 1 dichromate. Is going to yield 2 chromium 3 plus 7 H2O. Okay, I want to check to see if I made any mistakes here. And so when we check this, we check for atom balance. 14 H's, 7 times 2 is 14 H's, 2 chromiums, 7 oxygens, 7 oxygens. So the atoms are balanced. In addition to checking for atom balance, we have to check charge balance. So 6 electrons is minus 6 plus 14 is going to give us plus 8. Plus 8 minus 2 is going to give us plus 6. So I have plus 6 on the left, and then 2 times plus 3 is plus 6 on the right. Water's neutral. And so this is balanced. We call this a balanced half reaction. And in this case, we have the oxidizer here. This is a half reaction for the oxidizer. Oxidizers take electrons. So I have electrons here. So this is my OA. That's in the forward direction. These reactions are reversible. So in the reverse direction, chromium-3 is losing electrons over here. So this is the conjugate reducing agent. Here. Now, this half reaction is called a reduction half reaction, even though it's with the oxidizing agent. And the reason is because when the oxidizing agent reacts, it's reduced in the process. And so we go from chromium plus 6 to chromium plus 3. That's called reduction in terms of the electrons. All right, let's take a look at the other half reaction here. If this is the reduction half reaction, this must be the oxidation half reaction. And so we always save oxygen and hydrogen for last, so we're going to balance out the carbons first. So I have 2 carbons over here, 1 carbon over here, so I need to change the coefficient on CO2 to 2. And then we look at the oxygens. I have 4 oxygens on the left. I have 2 times 2 is 4 oxygens on the right. The oxygens are balanced, so we don't have to do anything. Then we look at the hydrogens. I have 2 hydrogens on the left and no hydrogens on the right. And so I'm going to have to add plus 2H plus. Then I balance out the charge. Oxalic acid's neutral, and then I have a neutral CO2 plus the H pluses and 2 of them, so we're going to have plus 2 over here. And so what I'll do is I'll add 2 electrons here. And this would give me my balanced half reaction, which is going to be oxalic acid goes to 2 CO2 plus 2H plus 2 electrons. So what's happening with oxalic acid is losing electrons. Oxidizers take electrons, reducers lose electrons. So this is going to be my reducing agent in the forward direction. If I go backwards here, this will be my oxidizing agent in the reverse direction. It is CO2 and H plus taking the electrons there. Let's check if it's balanced. So I check charge and atom balance. Let's do atoms first. 2 hydrogens, 2 hydrogens, 2 carbons, 2 carbons, 4 oxygens, 4 oxygens. Atoms are balanced. Charge balance, 0 on the left, CO2 0, plus 2, minus 2, 0. All right, the next step is I'm going to combine the 2 equations, making sure that the electrons cancel. So over here I have 6 electrons. Over here I have 2 electrons. So what I'm going to do is I'm going to multiply the second equation by 3. So that gives me 3 oxalic acids. And then 2 times 3 is going to be 6 CO2s. And then 2 times 3 again. It's going to give me 6H plus, and then 6 electrons. That should be okay. And now I can combine them. I need to make sure the electrons cancel. We cannot have free electrons in a chemical equation like this. And so the 6 electrons that were consumed here are canceled out by those 6 electrons produced there. We can also simplify the H plus. I have 6 H pluses here. Let's go ahead and get rid of those. And then I can take out 6 of the 14, which will leave me with 8 H plus. And so I'll have 8 H plus a dichromate plus 3 oxalic acids. This is going to yield 2 chromium 3 plus 7 H2O liquid plus 6 CO2 and that looks to be it. All right, let's check atom and charge balance for this equation. So 8 hydrogens plus 6 hydrogens, 14 hydrogens on the left. 7 times 2 is 14 hydrogens on the right. 2 chromiums on the left, 2 chromiums on the right. 7 plus 12, 19 oxygens on the left. 7 plus 12, 19 oxygens on the right. So it's balanced. And then the charge plus 8 minus 2 is plus 6. And then 2 times plus 3 is plus 6. So this looks good. Now, all skeleton redox have driving force. Otherwise, you can't write out the products without predicting them. And so the H plus and the dichromate, this is my oxidizing agent. This is my reducing agent in the forward direction. And then in the reverse direction, we have CO2 and we have chromium 3 in water. So the chromium 3 in the water, that's our reducing agent. And CO2 must be our oxidizing agent. Since all skeleton redox have driving force, we must be going from strong, strong to weak, weak. So in other words, dichromate in acid is a stronger oxidizer than CO2. Pretty much that's all right, so we're going to do a little bit of stoichiometry. Can you calculate for me how many grams of oxalic acid are required for this reaction? So we'll do calculation 1 here. How many grams of oxalic acid? The oxalic acid was a monohydrate. And so oxalic acid dot, I'll just say monohydrate. How many grams of oxalic acid monohydrate are required? How many grams of dichromate did you use? .6 grams was the amount that the procedure asks you to use. Instead, use your mass. All right, why don't you try this calculation here? I'll be right back. Okay, let's take a look at this calculation here. What did we start off with? We started off with use your amount. The procedure asks to use 3.6 grams. Our balances are more precise than this. Our balances read 2 decimal places. And so you got to make sure your masses are the 2 decimal places. So maybe it's like 3.60 or 3.65 or whatever you use. But what did we weigh out for the source of dichromate? So we needed dichromate for this reaction. Where did the dichromate come from? Yeah, potassium dichromate. And so it's going to be 3.6 grams of potassium dichromate. Was the potassium dichromate anhydrous or was it the hydrate? I think it was anhydrous potassium dichromate. And so we can calculate the molar mass. I'm going to skip the calculation here. Let's see if I can just look it up. And so I'm just going to go to Wikipedia and take a look at the molar mass of potassium dichromate. And the molar mass is 294.185. 294.185. per mole. That's the molar mass of potassium dichromate. And so the grams cancel, and that leaves me with the moles of potassium dichromate. In this equation, I have dichromate, not potassium dichromate, but we know that potassium dichromate is a strong electrolyte. Even if it wasn't, we know that for every 1 mole of dichromate ion, I'll need 1 mole of potassium dichromate. And so the moles of potassium dichromate cancel. That leaves me with moles of dichromate ion. And then I take a look at the mole ratio. For every dichromate, I'll need 3 oxalic acids. So for every 1 mole of dichromate ion, I'll need 3 moles of oxalic acid. Yeah, I'm going to add the hydrate in just a minute. So the moles of dichromate cancel. But the oxalic acid is going to come from oxalic acid monohydrate. And so I'll put in, for every 1 mole of oxalic acid monohydrate, I have 3, I mean, not 3, 1, I'll have 1 mole of oxalic acid. Okay, so now I have moles of oxalic acid monohydrate, and I can calculate the molar mass, but I'm just going to look it up. Oxalic acid monohydrate, this is from Chem, is 108.05. .05 grams per mole. So the moles of oxalic acid monohydrate gets converted into grams of oxalic acid monohydrate. And so if I have 3.6 grams of potassium dichromate, how many grams of oxalic acid do I need? So let's go ahead and do that. That's going to be 3.6 divided by 294.185 times 3 times 108.05. And I calculate 3.966 grams. How many grams did you use approximately? Or how many grams did it say to use? Yeah, procedure said to use 10. If I did the calculation correctly, then it seems a bit overkill, doesn't it? I only really need 4 grams, but I'm going to put in 10 grams there. Doesn't it seem like kind of a waste? Yeah. Yeah, that's a huge excess. And so it does seem like it's a waste. All right, so we have our dichromate, we have our oxalic acid. Now we need our H+. The H+ can come from oxalic acid, but we need, looks like we need additional H. And so we could add an acid here, another acid, maybe like HCl. But if we add HCl to give us our H+, then we're going to have chloride contaminating our mixture. But maybe we could wash off any chloride that gets stuck on the crystal. Instead, do you know what we're going to use for the H+? Why not use oxalic acid? Now, oxalic acid is a weak acid, so those H+ are going to be stuck on oxalate, but during the course of this reaction, the H+ can get knocked off. And the oxalic acid can react. So if we need an additional 8 acid hydrogens, and we're going to take it from oxalic acid, then that means we're going to need 4 more moles of oxalic acid. Does that make sense? Procedure says to use 10 grams, which seems way excessive, but it's not. And the reason is because we need additional H+, which we can get from oxalic acid if we add extra. And so really the ratio is, we're going to change this ratio here. We need an additional 8 H+. Since oxalic acid all right, this looks okay here. So we need an additional 8 H+. We're going to get those 8 H+ from the oxalic acid. So what that's going to do is it's going to change this conversion factor. And so to get that, I'll need an additional 4, oxalic acid being a diprotic acid. So each oxalic acid yields 2 H+. So if I need an additional 4 to give us an additional 8 H+, I'm going to change this conversion factor to 7 moles of oxalic acid for every 1 mole of dichromate. And that should give us the correct number of H pluses. Everything else is the same. So if we do this, how many grams does this come out to? And so I'm going to take the last number I had. Oops. Oh, shoot. 3.966. And then I'm going to multiply that by 7 divided by 3. And this gives me, I should use 9.254 grams of oxalic acid monohydrate solid to get that extra H plus. Does that make sense? And so how many am I using? Well, I'm supposed to use 10 for the procedure, which is excess here. But it's not an excessive amount of excess. It's just a little bit extra. All right, let's go to the next reaction. Actually, before that, that's how much I should use. So I have excess oxalic acid. What I'm going to do is I'm going to calculate my theoretical yield of chromium 3+. So why don't you do that? Calculate the theoretical yield of chromium 3+. Someone get it? What did you get, Tristan?
3.6 grams. It's 1.2726.
Of chromium 3+. Is that what you guys got? Okay. And so you set up the stoichiometry for that. All right, let's go on to the next reaction. So what we're going to do is we're going to take that 1.2726 grams of chromium 3+ and then react that with oxalate. And how many oxalates do we need? We need 3 oxalates. Oxalate's a bidentate ligand. And we'll have 3 oxalates to make the trioxalato complex. I'll use the abbreviation for oxalate here. Saves a little bit of writing. So where are we getting the oxalate from? This is from potassium oxalate. Now, was it anhydrous potassium oxalate or was it a hydrate that we use? Anhydrous. So let's calculate how many grams of potassium oxalate were required for this. Is it hydrate? Monohydrate? Thanks. And so I'm going to calculate the amount of potassium oxalate monohydrate required. What did you use for the molar mass of chromium? 52, 51.996, so I'll use the same. 51.996 grams per mole. That gives me grams to moles of chromium-3. And then we know we need 3 moles of oxalate ions, bidentate ligand, for every 1 mole of chromium-3. And then for every mole of oxalate, I need 1 mole of potassium oxalate, monohydrate. And then I need the molar mass of potassium oxalate monohydrate, and I don't want to calculate it, so I'm just going to look it up. Potassium oxalate hydrate, or monohydrate, is a chelating agent used in the pharmaceutical industry as a purifying agent and as a precipitating agent for rare earths. So let's see, I'll just go to NIST. Oxalate C2O4, so there's an extra H2O here. What's that negative sign there? That's weird. 145.13. So I need to add one more factor on here. 145.13 grams per mole. So how much potassium oxalate do I need to react 1.2726 divided by wrong molar mass? Okay. What did you get for the molar mass? Let me check another source. Yeah. K2 C2O4 H2O. So this works out 184.23. Okay. Let me fix that. All right. So 1.2726 divided by 51.996 times 3 times 184.23. I need 13.527. How much did the procedure say to use? Sorry, can you repeat that one more time, Tristan?
4.2.
Procedure called for 4.2 grams. Am I going to have enough? No. Excuse me. It would mean that oxalate's not the limiting reagent. It would mean that, well, actually, it would mean that oxalate is the limiting reagent. We don't want oxalate to be the limiting reagent. What do we want to be the limiting reagent? Chromium. So that's the problem. But procedure called for 4.2 grams. But it is not our only source for oxalate.
That's 2 minus.
We had another source for oxalate, and the other source for oxalate was from the previous reaction. What we used for the H plus here, we needed 8H plus. We ended up using 4 oxalic acids for that to give us 8H pluses. And this just uses the hydrogen. It doesn't use the oxalate. So this is actually 4 moles of extra oxalate that aren't being used. 3 of the 4, actually total would be 7. 3 out of the total 7 moles of oxalic acid, the oxalate's being used, it's going to be converted to CO2. 4 out of that will not be used. And so we have some additional oxalate from the oxalic acid, and that can react here. So the deficit doesn't doesn't look as bad as it is. So we'll take our chromium 3 plus, and normally we can just react this with oxalate here, C2O4 2 minus, and we'll take 3 of those here. Actually, let me just do 1 for right now. And what we're going to get is this. It's just going to be a chromium 3 plus with this bidentate oxalate ligand on here. And that's fine. We can fit an additional 3 more. But the situation here is we could have also used oxalic acid. When we look at oxalate versus oxalic acid, these are totally different in terms of Bronsted. In terms of Bronsted, this is a Bronsted base, this is a Bronsted acid. But in terms of Lewis, both of these can act as a Lewis base. And that is, what I can have here is I can have the chromium be attacked by oxalic acid rather than oxalate. So if that happens, let's say this lone pair attacks there, this lone pair attacks here. And then when that happens, the hydrogen leaves as a proton, leaving the bonding electrons behind. So we end up with something that looks like this. And then the two H pluses get knocked off. So both the oxalic acid and oxalate can react in the same manner. And so we aren't as bad as this. In fact, we have a lot of extra oxalate in there. And so the chromium should still be the limiting reagent. At least I hope it is. But what we're going to do is we're going to do something a little bit different for the overall stoichiometry. So that was reaction 2. Let's take a look at reaction 3. But what we'll do is we'll take a break and then we'll take a look at reaction 3 next. Okay, we'll start again here. So let's take a look at the reaction 3. The reaction 3, we had 3 potassium ions plus the trioxalato chromate 3 ion plus 3 waters. And then we add the ethanol, and that should precipitate out the potassium trioxalato chromate 3 trihydrate solid. So this is reaction 3. So when we do this, we're doing these 3 reactions, maybe 4 if you count the recrystallization step. Let's look at reaction 4. This is metathesis, and reaction 4 is metathesis as well. In reaction 4, we take the precipitate, which we filter out here, .3H2O solid, and then we dissolve that in a minimum of water. And what happens here is this dissolves. When this dissolves, it breaks apart the lattice. And frees up the water. And then we add ethanol, and hopefully you guys are getting crystals again. There. And the purpose of recrystallization was to increase the purity of our precipitate. Because each time we do this, we wash away more impurities on the precipitate. We lock them out from crystallizing. And we try to get bigger crystals. Your crystals might not. We'll take a look at them today and see if they've grown any bigger. And take a look and see if you've gotten crystals. But if we're having trouble getting large crystals, then we might do a recrystallization step 2 or recrystallization step 3. We might try doing some additional recrystallizations. And then just try to tweak the condition to minimize the formation of lots of little crystals and try to instead get a few big crystals which can grow. Now, our goal isn't to get a high yield. Our goal is to get a high purity. And so we're going to sacrifice some of the yield. But nonetheless, it's always nice to get a good yield, because if we get a good percent yield, then we're not wasting much. But when I do the stoichiometry, I don't want to do it step by step. It's a bit of a hassle to do the stoichiometry according to each step. And so we're going to do it overall. Let's see my note where I'm on. All right, so the overall stoichiometry here is, what we can do is we can add up all the reactions, i.e. combine all reactions. We actually don't even have to add up all the reactions, you know. Like if we were to add it up, then I'd go back up here and I see reaction 1 produces 2 chromium 3 pluses. So I go to reaction 2 and I'll adjust this, you know, rather than having 1 chromium, I'll put 2, and then I'll need 6, and then I'll form 2 over here. It's not going to change the ratio. You know, it's still a 1 to 3 ratio. Now it's a 2 to 6 here. And then I do the same thing over here. But overall, we can combine all the reactions. That's one. Or the easiest method is this. The easiest method is we look at what's happening with the chromium. We're trying to keep chromium as our limiting reagent because we don't want a whole bunch of, let me make sure I've got this recording. And therefore, here we have our chromium from the dichromate, Cr2O7 2 minus. And we want all that to end up in our complex. And so our complex is going to be K3 CrOX3. Actually, so I have 2 chromiums over here. I have 1 chromium over here. So the simplest way to balance it is just throw a 2 right here. Okay. And so that's going to give me my 2 chromiums here. I didn't have any other products which contain chromium. So all the chromium that I start off with in dichromate should end up as chromium in the complex. And so this is my mole ratio. So this is the easiest because I'll ignore everything else. If there are multiple products that contain chromium, then this doesn't work. But since I know that all the chromium that I start off with ends up here, then I'm okay. And so now I can just do the stoichiometry. 3.6 grams of potassium chromate. This is the anhydrous. And then convert that to moles. Was the molar mass 294.185. 294.185 grams per mole. And that gives me moles of potassium chromate, dichromate, excuse me. And then I know I have 1 mole of dichromate ions for every 1 mole of potassium dichromate. And so the moles of potassium dichromate cancel. That leaves me with moles of dichromate ions. And then I see that I'm going to have 2 moles of product, K3CrOX3.3H2O, for every 1 mole of dichromate. So this is kind of the combined. I didn't balance everything out. I just balanced the chromiums out. And since chromium was my limiting reagent, this should work. And since chromium only ends up in one product, this should work. Okay, then I just need the molar mass. So this, otherwise I'm going to be doing lots of stoichiometry. And so I'm going to look up the molar mass for potassium, the complex, trioxalato, chromate 3. And here it is. Potassium, oh, that's not it. That's not it either. So I'm going to look it up here. K3 CR C2O4 3. I'm just going to do the anhydrous here, see if it comes up, and then I'll add the waters to that. So I have K3. Here I have the potassium trioxalato chromate 3, and I want the molar mass. Here it is, but they want me to pay for this. I'm not going to pay for that. I might have to break down and actually calculate it. All right, go ahead and give it to me. 487.
487.39.
Thank you. 487.39 grams per mole. So that should leave me with grams of product. And so let's go ahead and calculate it. 3.6 divided by 294.185 times 2 times 487.39. And our yield should have been 11.928 grams of product. So we should get close to 12 grams of product. And so after we recrystallize it, we're going to wash their crystals, and then we're going to dry them and weigh them. And hopefully we get something close, but it's all right if we lose a bunch too, as long as we have good purity. Okay, so this is what we call the theoretical yield of product. And there could be lots of reasons we don't get that theoretical yield. Let's see. All right, I'm going to stop. We're going to continue with this because this is going to be a more involved report. And so there are different things that we're going to say about this particular experiment. What I want to do now is I want to talk about today's experiment. And let me pull up the lab here. So what we're going to do is we're going to do some manipulation of the equilibria. So here in the first one, we're taking copper 2. This is light blue. Now, if I have copper 2 aqueous, that could be the hydrate, you know. Well, it's not really the hydrate, it's the aqua complex. There's a difference between a hydrate, where waters are kind of stuck in the holes of the crystal, versus an aqua complex, where the waters are actually attached as ligands. So we could have hexa aqua copper 2 ions, aka copper 2 plus aqueous. That would be it. And then we could add some ammonia to this. Actually, we could add up to 4 ammonias. Seems like we should be able to add up to 6, but only 4 attach max. And what this forms is the tetramine complex, like this. Tetramine copper 2 ion. And this tetramine copper 2 is dark blue. And so we're going to add some ammonia to get this dark blue, or generate this dark blue. And this is reversible here. But eventually we're going to hit a stable ratio. That stable ratio would be the product over reactant ratio, which would be given by K, the equilibrium constant. Now, there are different things we can do to shift this one way. So once this is established at equilibrium, we can add more ammonia. So if we add more ammonia, then we have more reactant. If we have more reactant, what that's going to do is going to push. Even though we only have one of the reactants, not all the copper ions have reacted. And so even if we add just only the ammonia, that's going to get more of the copper to react to go and form this. Actually, this is quite downhill. Ammonia turns out to be an excellent Lewis base, especially for these types of reactions. It's not, the strongest Bronsted base. It's kind of a weak Bronsted base. This is it. And so that's one of the chemical properties of ammonia. It's a pretty good Lewis base. It's a weak Bronsted base. What are some of the other chemical properties of ammonia? As far as metathesis goes, ammonia can hydrolyze water, right? Ammonia can hydrolyze water to produce a little bit of hydroxide. And a little bit of hydroxide will result in a precipitate of copper 2 hydroxide. And so when you initially add the ammonia, what you get is a baby blue precipitate. But if you keep adding the ammonia, then the strength of this Lewis base takes over and it'll react preferentially with the copper. And so what eventually happens is this little light blue precipitate disappears with additional ammonia, because ammonia is an excellent Lewis base, and this is a stable complex here, the tetramine copper 2 complex. Now what happened? It went from 6 coordination to 4 coordinate. It really didn't. There are 2 waters still coordinated here, which we aren't showing. So oftentimes the water aren't shown, like in this, copper 2 plus aqueous. Where are the waters? Well, they're here, but sometimes we just don't show it. Okay, same thing over here. So we could add more ammonia, and what that does is it forces more of the reactant to react, and we end up doing this. We form more product. So this is called a shift right. And so this is Le Chatelier's principle. Le Chatelier's principle is looking how the equilibrium can shift left or it can shift right if you perturb it. So here we're perturbing it by just adding additional ammonia and shifting it right. But we can take advantage of some of the properties of ammonia. That is, it reacts in metathesis reactions, so we can throw in some other cations in here. Copper 2 hydroxide will eventually redissolve, but there could be other ones that form more stable hydroxides, like iron 3. Iron 3 hydroxide is extremely stable hydroxide. It's extremely stable hydroxide, but we aren't, because that's going to create kind of a mess. So what's a chemical property of ammonia? that we can do to get this. Well, one of the things we could do is we can add more ammonia or we can remove ammonia. Now, how do you remove ammonia? One way we might remove ammonia is let it vaporize off the surface. You know, ammonia is normally gas, but that would take a long time. What we're going to do is we're going to react the ammonia and remove it. And so we can remove it. And one way of removing it is by adding acid. So if we add H+, then the acid will react with the ammonia here to make ammonium. And ammonium is not going to participate in this, so adding acid is going to shift this left. So if we remove some of the reactants here, then we don't have enough reaction to compensate to keep or maintain a stable product concentration, and we're going to get some reverse reaction taking place here. So we're looking at shifting left and shifting right. This is easy to detect because this is light blue, this is dark blue, so we can see the change in color, which is fairly dramatic. Okay. All right, so this is our lab. What we're going to do is we're just going to use small amounts. This is very qualitative, so you don't have to worry. We can use the spot plate. The spot plate, I think, can hold like maybe a milliliter. A milliliter is 20 drops, so you can adjust the amounts. You can just test it to see how many drops it takes. But there we are. All right, so go ahead and get started. We'll need goggles for this lab. You can work with partners for this lab. It's just called Le Chatelier's second part, the Le Chatelier's lab.